Thank you so much for inviting me. Today, I will present some of my ongoing PhD work that's focused on space-time clustering of seismicity. And I want to start with some background on processes and mechanisms that drive rift evolution. So there are mainly two, weakening and strengthening processes. And in this case, we really care about the weakening process because it will facilitate rift evolution. And in particular, diking and faulting represent weakening processes that release strain. And as tectonic forces pull on the lithosphere, they build up elastic strain, and eventually, when it reaches a tipping point, it releases that elastic strain that has been built up. And strain can be released through two kind of distinct temporal patterns, cycles, which we could think of as like the earthquake cycle in faults, and pulses, which are often driven by magmatic fluids or diking. And we know that strain release can be seismic, aseismic, or magma-driven, but this can present a bit of a knowledge gap because in magma rift, sorry, diking is a dominant mechanism for release strain, but we see that from global maps that we have a lot of magma pore rifted margins where magma was absent and yet it successfully rifted apart. So this raises the question on how, in the absence of magma, how built-up elastic strain is being released in magma pore rifts. So the key science question for today is what are the driving modes of strain release in an active magma pore rift zone? And how we're going to look into this is going to be through special temporal patterns of seismicity that might provide critical insights into the dominant deformation mechanisms that are driving this strain release. So today I will focus on the East African rift system and more particularly in the magma pore branch of the western branch. And we will be looking at this black outline here, which is the Tanganyika-Rukwa Rift Zone, which encompasses the Tanganyika and the Rukwa rifts, just as mentioned. And in this southern section here, we will focus where there was a seismic array that was deployed, which is this greenish, bluish triangles. But first, I want to talk a little bit more about this area. So previous studies have shown that there's a high VPVS ratio in the crust. And those high VPVS ratios have been tied via crustal anisotropy to fluid in the lower crust, likely volatiles and partial melt. Some crypt-driven and fluid-driven seismicity has been found in Rukwa Rift. And also, blind melts have been proposed as a mechanism for the persisting weakening mechanism. So in this work, I leveraged pre-existing data that was collected in this region in 2014 by a Tanga 14 array, which I have displayed here in the purple triangles. And I applied a machine learning pipeline. So I used FaceNet to pick P and S waves, phases, and then gamma to associate them, and then located it. And from there, we obtained a catalog of about 5,000 events. How this compares this catalog, so we worked quite a bit on it. So here on the left, I have what was previously published, which is in 2019. And on the right, I have the new catalog with the machine learning enhanced pipeline. So we see a lot of seismicity where there was seismicity, which is a good sanity check. And we also get to see smaller events. So we have a lower magnitude completeness. We also really focused on the uncertainties in this. And I don't want to, you can ask me questions about it, but I will skip through this just in the set name of time. But mostly we focus on very high resolution, low uncertainty events. So to look at the spatiotemporal clustering, we then did cross correlation and double difference relocation, from which we obtained about 2,000 600 events that were very well located. And then we applied the clustering algorithm. And I briefly want to mention that it's an algorithm used by Global et al. In 2019, which uses the nearest neighbor spanning forest. And it's based on the algorithm by Zalapin and Benzain in 2013, which partitions seismicity from background events into trigger clusters. And it does that by evaluating the proximity in space, time, and the magnitude. And what's really important is that this method allows us to distinguish between independent kind of tectonic loading events and localized triggered sequence of swarm seismicity. So I want to talk a little bit about our results now. So here in panel A, I have plotted the centroids of the clusters, and they're color-coded by depth. And right off the bat, we see that we have way more spatial-temporal clustering in the Tanganyika Rift compared to the Rukwa Rift. And I have plotted two cross-sections, A that goes through Tanganyika, A to A prime, and B to B prime that goes through Rukwa. And these have been color-coded by total duration of the clusters. So the black ones are clusters that have a duration of about a day, and then the yellow ones are clusters that have a duration of about 2 months. And first of all, we see, quite a range of times in these clusterings, but some of the key points I want to make here is that we interpret these longer duration clusters as kind of fluid-driven seismicity, and we see that it's pervasive throughout the rift zone. So we see them both in Tanganyika and Rukwa. We interpret it to be likely volatiles from the mantle, and we also see a bit of a higher occurrence of fluid-driven seismicity in the regions where there's the greatest crustal thinning. And if we look a bit more closer into these clusters, like what exactly do they entail? These clusters have different geometry and time evolution. So here at the top panel, I have the clusters once again, but this time they're color-coded in such a way that in the lower panel, you can see the individual events that encompass that cluster. And I once again have plotted the A to A prime and the B to B prime cross sections. And then the triangles are the mojo from an independent 2017 study. But here, different colors are different clusters. So we can start to see what each cluster looks like. And we can also take a sense of, for example, the cumulative number of events by time. And we see that all of these clusters seem to have different behaviors. And today, mostly in the interest of time, I will only focus on two. The first one will be this green one here, that is the largest we have in this data set, which corresponds to this cluster here in Rukwa, and is also the largest cluster in Rukwa Rift. So this is a GIF where I'll play it a couple of times, but what you see here is, well, multiple things going on. But this panel here is the map view, so you get a sense of in map view what is happening. These are two cross sections, an east-west and a north-south cross section, and then this is being plotted by depth and the time. So depth are like the events, and it's all color-coded by the day since the start of the cluster. In this lower panel here, we have the total events as they go on. And then in the lower panel here, we have the magnitude with time. And I will play it once again. Oh, there we go. So it starts, and then we see all this kind of swarm seismicity appear. And then we have another pulse. And here, one of the key takeaways that I want to focus on is that we see kind of three pulses, this first initial pulse, this second pulse, and then this later pulse. So we observe distinct pulses of swarm seismicity, we also observe that they're like pipe-like geometry from the cross sections. We see that they go pretty up, they move upward. And all of these suggest that it's fluid-driven seismicity, probably volatiles. And we also see transient stalling of deeper reservoirs. So it seems like it hovers for a little bit and then it shoots up and then it recharges, it hovers again. And this pulses and stalling of sort of seismicity suggests that there might be distributed reservoirs in the lithosphere.
Actually, you're at 11 minutes now.
Okay, perfect. Thank you. And now I want to focus on the second cluster that for today, which is the largest cluster in the Tanganyika Rift, which is this or dark orange one here, which would correspond to this one here. And once again, we see, I will just let it play for a few seconds. But once again, we see the progression and evolution of migration of this cluster. And some of the key takeaways I want to focus is that we observe distinct pulses of storm seismicity. Oh, and that this is in Tanganyika, similar to the Rukwa Rift, but this is Tanganyika Rift. We see upward migration, which once again suggests the pipe-like geometry, and we see no stalling observed at deeper depth. And then very briefly, I will mention that we also see no distributed lithospheric volatile reservoirs and no stalling, where we see that where the crust is actually thinnest. So that is pretty interesting. And I just want to briefly go through the implications of this. So I know we only looked at two clusters in the due to time, but we can get a sense of what the plumbing patterns might be for each system. So in the Rukwa Rift, we see the distributed volatile reservoirs in the lithosphere, which suggests a greater residence time for mantle source volatiles. And the Tanganyika Rift, we see a more direct plumbing from the mantle to the shallow crust based on the observed seismicity. And this can give a little bit of hints about helium-3, helium-4 ratio and the sources of it. So this is future work, but we hypothesize that there might be a dominance of mantle source volatile degassing at the surface in Tanganyika Rift due to the plumbing system that we seem to observe in the seismicity. And very briefly, I just have a couple of summaries. So we see that machine learning can significantly improve earthquake catalog, especially in underestimated tectonical active regions. We see pervasive fluid-driven seismicity across the Tanganyika Rift Zone. We observed pulses and stalling patterns of storm seismicity, which might suggest distributed reservoir in the Rukwa Rift, but absent in the Tanganyika Rift. And then some distributed volatile reservoir, like regions in less thin lithosphere, which is surprising compared to those of significant thin lithosphere. And some ongoing work is that we're gonna, I'm currently applying some template matching to find even smaller events so we can capture even more subtle patterns in those clusters. And I think with that, I am done. I'll take any questions. Thank you.
Thanks a lot. The floor is open for questions. And I would start with the first question. Where did you, which surface expressions can be measured in terms of the volatiles that you showed us? How many springs have been sampled? How many degassing sites are
That's a good
known?
question.
Where did you get the data from?
Yes, so the Tanganyika Rift, I believe, is there's I have not seen any published work that I can think of on top of my head about springs being measured, but I know the Rukwa Rift has quite a bit. The most recent one I've seen samples Rukwa, but kind of not the southern part where Rungwa is, but the kind of central parts. But I believe there's soon to come out studies on the spring chemistry in the northern part of Rukwa.
Okay, thanks. Kim has a question.
Hi, great talk. I have a question about the clustering. So you mentioned that you use machine learning to identify your arrivals. Did you also
Yeah.
use the machine learning to determine your clustering, or was that
No.
basically? manually done?
Well, yeah, yes, that's a good way to put it. Yes, yes. So I used the Goebel et al. Algorithm, which is used to track fluid-driven seismicity in Oklahoma, kind of induced seismicity. And then it's public code. It works really well. And I just took that and applied it to this region. Yeah. So I didn't do any machine learning for the clustering itself.
Okay, so do you have some flexibility into how many clusters you actually identify? Or that was like you had 12-ish or something. Was that the maximum you could find?
No, that's a very conservative because I only looked at clusters that had more than 5 or 6 events. And then you can also play around with the magnitude completeness. If you go a bit lower, then perhaps you'll start to capture a little bit more noise, but perhaps you'll get more swarms too. So you can play around with those values too. Yeah.
And how much does that change your little cartoon like temporal evolution if you adjust your clusters to be less conservative?
Yeah, so from playing around, it seemed like it was pretty stable because otherwise it becomes noisier and then you cannot really see as much. It's not as nice.
Cool, very cool.
Yeah, awesome. Thank you.
We have time for 1 or 2 more questions. Amir, you're next.
Okay, thank you. So your study shows that there are distributed reservoirs within the crust in Rukwa Rift, but not beneath Tanganyika. So I assume they are close by, and what causes this difference? Why in one case you have pipe-like geometry for the seismicity to occur on the other side? Why there is this kind of distributed reservoir formation?
Yes, that's a good question, and that's something that I'm still thinking about. Yes, stay tuned.
Okay.
I would have a follow-up question. What are these distributed volatile reservoirs and how are they different from just normal volatile pathways?
I see. So we're thinking more that it's distributed in the sense that it seems to be somewhat vertically partitioned. So there seems to be kind of some recharge going on kind of at the upper mantle level below the moho, and then it goes up into the the lower crust, and it stalls there a little bit too. So I think we're referring more to distributed in the sense that it seems to pulse, like it stalls and it pulses and it stalls and it pulses, instead of what we saw in Tanganyika, that's just a somewhat straight upward migration, no stalling.
Okay, great. Well,
Yeah.
thanks again
Sasha?
for. Oh, yes.
Is there time for a quick, it's not a question, it's more a suggestion.
Well, just go ahead. Well,
Yeah, I don't know how much can I alert other papers here, but there is a paper from 2025 with about helium ratios around Lake Tanganyika.
Oh, okay.
Yeah,
I had not
as I
seen it.
heard that you,
Oh,
yeah.
oh, wonderful. Could you share the paper in the group chat?
If it's okay for Sasha and the others,
yeah,
yeah, for sure.
absolutely. That's
Oh,
what
that's
that is
wonderful.
there for.
Okay. Yeah, so it's my bad. I stand corrected.
No, definitely. Okay, thanks a lot and nice talk.